Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Syahira binti Muhammad Saleh. I would like to present about the problem-oriented problem-based learning project. Control system DAE 32103. It's about proportional integral derivative PID controller. So for the presentation highlights, we have introduction, result and discussion, and conclusion. Group members, me, Nur Syahira binti Muhammad Saleh, Deva Balan, Siti Asiah, and Nur Elisa Muiz. For the introduction, why implement PID controller? The PID controller is widely employed because it is very understandable and quite effective. Once attraction of the PID controller, that is, all engineers understand conceptually differentiation and integration, so they can implement the control system even without a deep understanding of the control theory. Further, even though the compensator is simple, it is quite sophisticated in that it captures the history of the system through the integration and anticipates the future behavior of the system through differentiation. We move to the next point. The application of PID controller in the industry and domestic use. The best PID controller application is temperature control, where the controller uses an input of a temperature sensor, and its input can be allied to be a control element, like a fan or heater. Generally, this controller is simply one element in a temperature control system. The entire system must be examined as well as considered while choosing the right controller. First of all, as you can see, the temperature controller of furnace. Generally, furnaces are used to include heating as well as hold a huge amount of raw material at huge temperatures. It is usually for the material occupied to include a huge mass. Consequently, it takes a high quantity of inertia, and the temperature of the material does not modify rapidly even when huge heat applied. Besides, for the second application is MPPT charge controller. The voltage current characteristic of a photovoltaic cell mainly depends on the range of temperature as well as irradiance. Based on the weather conditions, the current and operating voltage will change constantly. So it is extremely significant to track the highest power point of an efficient photovoltaic system. Last but not least, the converter of power electronics. We know that converter is an application of power electronics. So a PID controller is mostly used in converters. Whether a converter is allied through a system based on the change within the load, then the converter's output will be changed. For instance, an inverter is allied with load. The huge current is supplied once loads are increased. Thus, the parameters of voltage as well as the current is not stable, but it will alter based on the requirement. And for the last point, example of controller other than PID controller. It is fuzzy logic controllers, FLC. Fuzzy logic controllers are used where systems are highly nonlinear. Generally, most of the physical systems or electrical systems are highly nonlinear. Due to this reason, FLC are a good choice among researchers. An accurate mathematical is not needed in FLC. It works input based on past experience, can handle non-linearities, and can present disturbance insensitivity greater than the most other nonlinear controllers. That's all. Thank you.
Hello everyone, my name is Deoparan and I'll be explaining about the results and discussion for the project. So, I'll be explaining about two transfer functions, transfer function 1 and transfer function 2. So, these are the results. So, for the first activity, we will do it in MATLAB command. So, after we do it in MATLAB command, I have got an overshoot of 200 and settling time of none, because this is a marginally stable system. So we can see that this transfer function is a marginally stable system without implementing PID. So this is the graph, and the steady state error is infinity, as we can say that there's no settling time, and the wave is not settling, it's going in a marginal way in the same speed frequency. So for question 6, we are going to implement PID controllers, but for question 6, first we're going to implement a P controller. So we'll set up P in different values, which is 1, 10 and 100. As you can see in this table, the overshoot is same and the settling time is also same. As for steady state error, is also same because the P controller does not significantly change the system, so it remains the same. Next, for question 7, we are implementing KD, we are implementing PD. So we are implementing P controller and the D controller. After we're using that, we can see that the graph is going, the system is getting kind of stable, but not stable enough because the steady state error for each one of them is still infinity, and the overshoot, we can see respectively, is 85.8, 124 and 121. The setting time is 0. For question 8, you can see that you have to implement both all three PI and D controllers. So we have taken the best P, the P is 100, the best D is best D is 25, and we implement KI as we have three values, 10, 5 and 2. So as you can see this, we can see that the best value for the I is 10. You can see the overshoot for 10 it has the lowest of 7.64, the settling time as 0.191, and the steady state error of 0.99. So as you can see here, it is coupled with every single design, so requirements, and this is the final graph. As you can see here, this is the final graph of this system after implementing PID. As for transfer function 2, it's the same, but it's kind of different because this is a stable system. So when we run the Simulink model in MATLAB, you can see that it's a stable model, and it's in the underdamped model because it's from big to small, and the setting time is 13, and the overshoot is 98.6. Steady state error is 0.2. For question 6, as you see, we repeat every single step for each transfer function. And we can see that for question 6, for just only P controller, these are the values, and the best value was 500 as overshoot as 98.6, setting time 13, and has the lowest steady state error, and we want the lowest steady state error as that is what we need to compare with the final desired value. Question 7, we implement a PD controller, and the best value of a PD is 150 as the settling time, it has the less settling time. Then when we go into PID, when we implement I controller, we can see that the value of 30 with the I30, the overshoot has 4.56, settling time is 0.07, and steady state error is 0.2. This gives us the best graph system. That means that this system will be stable after implementing PID controller, and this is the final graph. As you can see here, it's an underdamped, stable system. So, as for the formula we have used to find the steady state error, the formula we have used is reference node or 1, the desired value is 1 per 1 plus Kp. So, we just do that formula and we get the steady state error, then we times by 100 to get the percentage. That's all.
Okay, so right now we will move to the next transfer function, which is the transfer function number 3. So the given equation is 1 over 0.8 square plus 2s plus 200. So for this transfer function, it was the same like the transfer function before. We already implemented it in the Simulink and got the graph from the scope. So from the graph, we have calculated the overshoot, setting time, and the steady state error. So for the overshoot, we got 87.6%. The setting time is 3.09 seconds, and the steady state error is 0.14%. So for the calculation that we have done, we can see that the system is stable, which are underdamped. Okay, so let's move to the next question. The next question is the same. We have to choose 3 different value of Kp. So in this transfer function, we choose the value of Kp are 100, 250, and 500. So we have take a look at the overshoot percentage, setting time, and the steady state error, and we have tabulate the value. So we move to the question number 7. In this question, we have been asked to keep one of the best value of Kp. So we choose the value of Kp 500. So and we have been asked to choose 3 different value of Kd. So we keep the Kp value 500, and then we change the Kd value to the 3 different value, which are 100, 50, and 20. So from this value, we have implemented it in the command window, and we have take a look at the overshoot percentage, settling time, and the steady state error. So we can see that the different value are recorded in the table. So let's move to the question number 8. So in this question, we have been asked to keep the best value of Kp, the best value of Kd. We only have to vary the Ki value. So we choose 2 different value of Ki, which are 550, 750, 950. So we have calculated the overshoot, setting time, and the steady state error. So after we have take a look at here at the value, we can see that the value, we can see that which value of Kp, Ki, Kd of PID controller are the best. So let's take a look at question number 9. So for this question, we have been asked to implement the PID controller or PD controller or PI controller. But for this equation or for this transfer function, we have choose to build the PID controller. So using the 3 best value of Kp, Ki, and Kd. So after we implement it, we can see the more stable system. Let's take a more close look at the graph that we have implemented using the PID controller. So we can see that the overshoot is only 2.7, the settling time is 1.93, and the overshoot we can calculate it using the formula 1 over 1 plus Kp. So after we have implemented the PID controller in the command window, so we have done with the equation with the transfer function number 3 for the last transfer function, which is the transfer function number 4. Okay, let's look at the equation. Okay, the given transfer function equation of transfer function number 4 is 7 over s to the power of 3 plus 3s to the power of 2 plus 2s. So from this transfer function, we have already built it in the Simulink, and this is the graph that we got from the scope in Simulink. Okay, from this graph, we can see that the system is unstable. So after we have determined the stability of the system, We have calculated the overshoot, settling time, and the steady state error from the graph. The overshoot percentage, settling time, and steady state error we have calculated using the formula. So we've got the overshoot of the system of the transfer function is 13.69, the settling time is 2.67 second, and the steady state error is infinity. So we move to the next question. So the next question asks to implement the ID controller to the original closed loop system. So start with KD and KI to 0 and then vary the proportional coefficient only. So try three different KP values, observe, record, and tabulate the overshoot, settling time, and steady state error. So in this question, I have choose three different value of KP, which is 0.18, 0.19, and 0.20. And we have calculated the overshoot percentage, settling times, and steady state error percentage. So from this table, we can see that with increase in the value of KP, 0.18, 0.19, and 0.20, the overshoot is increases 21.7 up to 25.3. Also, there is decrement in the steady state error, which are from 0.85 down to 0.83. So, but there were small changes in the settling time. Only small changes happen in the settling time regarding the value of KP value. We've looked at the next table. So the next table, the question asks to set the KP value. Okay, choose one, the best value out of the three values that we have chosen, and set KI to 0. Vary the derivative coefficient KD and try three different value of KD. So the same thing we do on this table. It's just that we keep the KP value the same. We use the 0.18 because it have a lower percentage overshoot and settling time only 12 to 21.7, and then we choose three different value of KD, which are 0.16, 0.17, and 0.18. Okay, when we simulate the transfer function, what we got is that the overshoot percentage we have calculated, okay, and the settling time, also the steady state error. So from this table, we can clearly see that increase in the value of KD from 0.16 to 0.18. We can see that there is a very small changes in the overshoot and settling time, but there is no change in steady state error. So, how we get the steady state error percentage? We use this formula 1 over 1 plus KP. For this transfer function, we only implemented the proportional and derivative controller in the system because with these two controller, the system has already stable, so we don't need to add the integral controller in the system. So the best value of KP that we have choose and the best value of KD that we have choose are for KP is 0.18 and for KD is 0.16. We have implemented controller in the transfer function. So we have done it in the command window and we got this graph. So from this graph, we can see that the settling time is 3.84 and the overshoot percentage is only 1.36. So what we can see here is that the system is stable and it fits the condition that the question has asked. So we have done with this transfer function number 4.
Hi, Assalamualaikum. My name is Nur Insam Isbindi Muhammad Zaini with matrix number EE190210. So today I'll be presenting about the part 3 for the conclusion of this project. So let's move to another slide. So before we decide which controller that performs best for each transfer function, I would like to summarize the function of each controller. So the first one is proportional control. So for the proportional coefficient, it is produced by an output value that is proportional to the current error value. So the response is just adjusted by multiplying the error by a constant Kp that called the proportional gain constant. So a high proportional gain results in a large change in the output for a given change in the error. So if the proportional gain is too high, the system can become unstable. whereas a small gain result in a small output response to a large input error and a less responsive or less sensitive controller. So if the proportional gain is too low, the control action may be too small when responding to the system disturbances. So the proportional term should contribute the bulk of the output changes. The next one is the integral control. So the integral in PID controller is the sum of the instantaneous error over time and gives the accumulated offset that should have been corrected previously. So the accumulated error is then multiplied by the integral gain, which is Ki, and added to the controller output. So the integral term accelerates the movement of the process towards the set point and eliminates the residual steady state error, which occurs with a pure proportional controller. However, since the integral term responds to accumulated error from the past, it can cause the present value to overshoot the set point value. So the last one is derivative control. So the derivative coefficient is a process which it calculated by determining the slope of the error over time and multiplying this rate of change by the derivative gain, which is KD. So the amount of the contribution of the derivative term to the overall control action is termed as the derivative gain, KD. The derivative term slows the rate of change of the controller output. So derived control is used to reduce the magnitude of the overshoot formed by the integral component and improve the combined controller process stability. So in each transfer function, we use this control, the derivative control. And however, the derivative term slows the transient response of the controller. So the differentiation of a signal amplifies noise, and this term in the controller became sensitive to noise in the error term and can cause a problem to become unstable noise, and the derivative gain are sufficiently large. So to conclude the overall control, we would say that the control that performs the best for each transfer function is the PID controls, because we use the PID control system for each transfer function except for the transfer function 4, which is it's only used through two controller, which is proportional and also derivative. So to conclude, PID control perform best is because its algorithm consists of three basic coefficients, which is proportional, integral, and derivative, which are varied to get optimal response. Even in the industry, the proportional integral derivative PID control is the most common control algorithm that has been used, since it is a robust and simple algorithm and universally accepted in industry control. Besides, it can be attributed partly to their robust performance in a wide range of operating conditions, and partly to their functional simplicity, which allow us to operate in a simple and a straightforward manner. Other than that, PID control performance measured in this control loop transfer function can be expressed both in time and also in the frequency domains. So it forces feedback to the match point, and sometimes error between feedback and set point is caused by set point change, but it is not adjusted much because in error in a loop is caused by disturbances in measured feedback. That's all from us. Thank you.